Hello, learners, and welcome to our second part of organic chemistry. So just like before, I wanted to remind you of some things that could be helpful to your learning process. What is that? The pre-lectures, one-pagers, and the previous information section. So any lecture portion, you have the pre-lecture, lecture, and post-lecture. Okay? I want you to make sure that you're focusing on that one-pager to orient your brain, and also reviewing any previous information. So that's going to be the concepts you see here. You can complete practice problems with those concepts. And the goal is that the lectures are going to enhance our pre-lecture, information. Don't forget, you also see those flashcard moments throughout the lectures as well. Okay, that's your way to say, hey, let me just stop and make sure I understand what I see right here. Make sure I write it down and stay active. Okay, so now let's get started. All right, folks, so welcome to the organic underworld, which is basically ran by hydrocarbons and the 8 families. Okay, this is going to be a place where certain families are more reactive than others and can break and build bonds to react and create new properties. But organic chemistry is made up of a few dozen families of functional groups, which are all based on having similar structural features and similar chemical reactivity. And so as you can see, we have so many different that we're going to focus on, about 14. Now, 6 of them we're going to group together as hydrocarbons, which we see here, and the rest of them we're going to call, of course, functional groups or family, which we will see the 8 later on. And as you can see, they have all of those carbon-hydrogen, carbon-carbon, and carbon attached to any halogens or heteroatom bond, right? And of course, those carbons, we're talking about organic compounds, so I'm bringing back that definition. Those carbons have the ability to catenate. So you can see them in different rings, like you see here. You can see them attached to, of course, with different branches and chains. So we have some branches here, and then we'll see some chains as we go along as well, and other branches too. And of course, depending on the reactivity or their properties, they are broken into and organized into these different families. Okay, folks? So a functional group is going to be a portion of a molecule that is recognizable or can be classified. So if I'm looking at this haloalkane, for example, there's an R group, which again we've seen as our carbon-hydrogen. It only has carbon-hydrogen and carbon bonds, so very unreactive. But then we have this X attached, which is going to represent a halogen. And so because it represents the halogens, that means that anything that has a halogen attached is going to create a brand new family called the halocanes, and that is going to be a functional group. So essentially you have a functional group. It's going to create new properties, okay, which means that you're going to have a new function. And no matter where you see the type of family created, they're always going to behave the same way chemically. So if I see a haloalkane or if I see a halogen in any other portion of organic compound, that halogen is going to react the same as any other halogen. So for example, if I have chlorines, the chlorines are going to react the same. We know that the halogens are a similar grouping as well on the periodic table, so it will have the same chemical behavior. But for our brief introduction today, we're going to be just describing these compounds in that group of hydrocarbons, and then again, those 8 families. Okay, folks? So just keep that in mind. All right, so meet the hydrocarbons. Of course, they're so named because they're made up of hydrogen and carbon, and will be our introduction to the organic underworld. Okay? Again, they're going to be made of those carbon-hydrogen bonds and carbon-carbon bonds. They include all of these different hydrocarbons here. So we have our alkanes, which are carbon-carbon single bonds, our alkenes, carbon-carbon double bonds, our alkynes, carbon-carbon triple bonds, and then our aromatic compounds, which are 6 carbons that are flush with, of course, double bonds, okay? And it's not just double bonds, it's actually a repeated pattern of double bonds and single bonds that resonate, that make them so specific and special. Now, with the alkanes, you also can have cycloalkanes and haloalkanes, and we'll talk about those other groups as well. Now, with these hydrocarbons, they can be saturated or unsaturated. So what does that actually mean? Saturated means that the compound contains carbon-carbon single bonds that are going to be sp3 hybridized. So when you're thinking about this group, you're thinking about things that are sp3 hybridized. Of course, with the double bond, it's going to be sp2 hybridized, and with the triple bond, it's going to be sp hybridized. With the aromatic compounds, you're not really focused on the hybridization because you have a mixture of chemical bonds. So when you're thinking of these hydrocarbons, you can automatically start trying to organize them. You say, okay, well, I can organize them into those that are going to be our single bonds here. Those are going to be double bonds. Those are going to be triple bonds. And of course, our aromatics. And that's going to be one way that you can start organizing things. Of course, you will see a flashcard moment. So that means you want to stop. You want to create a flashcard that can have, like, say, hydrocarbons on the front and then a way to classify them on the back. Now, I said that saturated means that you're going to have carbon-carbon single bond. And they're saturated with hydrogens, meaning each carbon has the maximum number of those 4 bonds, but they're all going to be hydrogen bonds as well, and they're all single, okay? Now, I'm going to write saturated here, and you know we're talking about carbon-hydrogen bonds and carbon-carbon single bonds. Now, we also have our double and our triple bonds. These are both going to be unsaturated. And unsaturated means that because we have a carbon-carbon double bond and a carbon-carbon triple bond, we do not have the maximum number of hydrogens surrounding each of these individual carbons. So when that happens, you have unsaturation. And when it comes to saturation, figuring out if something is saturated or unsaturated, you actually can understand the amount of carbons based on these little generic formulas. And we'll see these generic formulas as we go along, but these formulas are basically telling you how many hydrogens you can have based on the amount of carbons. So let's say I have 12 carbons, okay? And I have all single bonds in that carbon. So what is the maximum number of hydrogens? I'll have N, and these little generic formulas is equal to the number of carbons. So I have C12H, 2 times 12 plus 2, which is going to give me C12H26. So that means with 12 carbons in a hydrocarbon that is sp3 or all single bonds, or you can also say an alkane, you can actually have up to 26 hydrogens. Okay, now those hydrogens are going to decrease as you increase bonds. So with double bonds, of course, you don't see the added 2 here. With triple bonds, you see a -2 because you're going to be decreasing the amount of hydrogens as you change your saturation. So saturated, maximum amount of hydrogens. Unsaturated, of course, is going to be the least amount of hydrogens that you're going to have for those bonds. And remember, these are just all classifications to help you organize the information about these organic compounds. And sometimes that's going to influence the details of how you remember. So for example, you can just say, okay, this is an alkane and they're all single bond. Or you can say this is a saturated alkane, just adding in that extra layer of information that we talked about with saturation. Now again, how do we organize this? We have our carbon-carbon single bonds, we have our carbon-carbon double bonds, our carbon-carbon triple bonds, and of course our aromatics. That's going to be the first way that we are organizing them and breaking them down, just by the types of bonds that they make. Now with aromatics, they have both carbon-carbon bonds and carbon-carbon double bonds that are alternating. What that means is they provide resonance. So if I have this bond here and have the ability to be here, this one can be here, and this one can be here. So they continue to resonate. And the fact that you have the single bond, double bond alternation means that you're dealing with an aromatic compound. The fact that you have all single bonds means that you're dealing with the alkane hydrocarbon. When you have double and triple, again, that's just adding layers of information to help us kind of organize all of these different families. And we will see as we go along, of course, how some families are going to become more reactive because carbon is bonded to something other than a carbon or a hydrogen, for example. Okay, folks? So it's really about making that organization, right? So how do we start? Like anywhere else, we ask questions. We're going to get into learning the types and uses of hydrocarbons and, of course, naming them. And then we're going to use the same kind of strategy to go ahead and go further later on to name those 8 families as well. Again, our focus are going to be these 6 hydrocarbons. And when we look at something like haloalkane, this is all written with the R group here. Just remember that that R group represents a portion of the organic molecule that's mainly going to be made of carbon-carbon and carbon-hydrogen bonds, which are relatively non-polar. And so therefore, it's going to have, of course, not going to be a part of reactivity. That's what I'm trying to say. It's not going to be part of anything that's reactive because it's non-polar. You'll be seeing that our hydrocarbons in general are normally going to be non-polar when they're made of those carbon-carbon and carbon-hydrogen bonds. So with all these different chains and have all these carbon-hydrogen bonds here, carbon-hydrogen bond, carbon-hydrogen bond, and carbon-carbon bonds, for example, you'll see that they will all be non-polar or insoluble in water.